Today I will talk about Arya, a scalable approximate graph pattern mining system. This is a joint work with Kan Wu at University of Wisconsin-Madison and my advisor, Professor Alan Liu at Boston University. Nowadays, graph structured data are ubiquitous. Such kind of big data sets can be found in the social networks, biology domains, and so on. For example, the Twitter graph can already reach 10 billion edges in 2016, and a protein-protein graph can have 250 million edges. An important graph analytics task is the pattern mining. It has many real-world applications. For example, in the social network, it can be used to spot the connections between users and contents and do the advertisements based on this. Also, in biology, it can characterize protein-protein structures or the interactions. Also, in finite domain, it can do money laundering detection. Here is a simple example. This is a simple transaction graph, and the end nodes are the users and the banks. The edges represent the transactions between them. Users can do deposits money into the bank or withdraw some money from the bank. And a simple pattern example is that if a user performs small deposits followed by a large withdrawal, represented as the pattern can have 4 nodes, and with 1 node is the user, the other 3 end nodes are the banks. And such kind of user can be detected as the fraudulent user. To detect that, finding such kind of pattern in the transaction graph is the task called graph pattern mining. More formally, graph pattern mining focuses on finding all subgraph instances matching a given pattern of interest. For example, we may want to find the triangle instances in the 5-node graph, and a graph pattern mining algorithm will output all the subgraph instances matching the triangle. As highlighted here, there are 4 triangles. And in this work, we focus on counting the number of ending subgraphs. Existing works falls into 2 parts, the exact mining solutions and the approximate ones. Exact mining solutions are to iterate every isomorphic subgraph. For example, it will start from the very simplest part in the graph, just 1 node, and then it will expand from the simplest part with the neighbor list until it enumerates every combination of 3 nodes in the graph to see whether they can form a triangle or not. The pain point of exact mining solutions are they need to deal with exponentially growing intermediate candidate sets in terms of computation and storage. And recent works has many optimizations, including reducing the redundant enumeration and also system optimizations using hardware accelerators like GPU, but the problem of exact mining is still NP-complete. Even with a bunch of optimizations, it's still challenging to scale for the exact mining solutions. Here are some concrete numbers. Our BASC is the first general graph pattern mining system that uses several techniques to reduce the intermediate data sets. However, it needs several hours to mine a simple pattern, the 3-motif pattern with 3 nodes, on a graph with about 1 billion edges. And a more recent work, GraphPy in the HPC community, to mine a triangle-triangle pattern, which is more complex with 6 nodes. It needs more than a day to mine on a graph with a similar size. And we can see through years of optimization, it's still hard to scale for exact mining systems. However, we do not always require 100% accuracy in pattern counting, and many mining tasks do not need exact answers. For example, it doesn't need to output the density of certain patterns or output the representative subgraphs, but not all for the large graph inputs. In recent years, there are many approximate pattern mining algorithms proposed, and the general approximate approach is that to sample a subset of the input data and estimate the count based on the probability. Given such kind of sampling approach, ASAP is the first approximate pattern mining system that uses neighborhood sampling. Using the neighborhood sampling, here is some concrete steps of ASAP. First, we will sample an edge from the graph, and then sample a third node from the edge's neighbor list. Next, see whether the 3 nodes can form a triangle or not. And each part here is a sampling trail. We can calculate the probability of each sampling trail, and since the graph here is symmetric, the probability of each sampling trail is the same. For example, the first part comes from there are 8 edges in the graph, and the sampling one edge probability is 1/8. And there are 4 neighbors, including the repetitive ones of an edge, so the next part of the probability is 1/4. Then based on the inverse probability, we can see each sampling trail can form a triangle or not. Then we can give the triangle counting estimation. And finally, by combining all of them together, we give the estimated triangle counting results. In the ASAP paper, it shows that it can give up to 258 times speed up compared with exact mining solutions. However, ASAP cannot scale to complex patterns. On a 16-machine cluster mining the 5-house pattern with 5 nodes and the Twitter and UK graph, it needs 10 to 20 minutes with the 5% or 10% error target to finish the job. And this is because ASAP needs larger number of samplers for more complex patterns. For example, from extending a 4-node pattern to a 5-node pattern, there's a bigger delta increase in the number of samplers needed. Here, the delta is the maximum degree of the graph, and it can be large, for example, 1,000 or more in the Twitter graph. So if the patterns are more complex and we keep sampling them as a whole unit, the approximate mining solution needs significantly more samplers, and then it's less scalable. So instead, we ask the question, can we reduce the complexity of the sampled pattern and potentially reduce the number of samplers needed? And our key idea is to leverage graph decomposition theory to decompose complex patterns into simpler ones and sample them individually to reduce the complexity of the sampling. The powerful graph decomposition theorem says that solving an optimal fractional edge cover can decompose any patterns into a collection of odd cycles and stars, which meets the optimal bounds for sampling arbitrary patterns. Here is a complex pattern example, the 5-cycle and 5-star pattern. So the optimal fractional edge cover linear programming solver, it will assign some weights to the edges that form the edge cover. And here, for example, it will assign 0.5 weight to the cycle edges and 1 weight to the star edges. Based on this, the complex pattern is decomposed into the odd cycle and the star pattern, these subpatterns. This is the basic graph decomposition algorithm, and based on this, we have several steps to do the sampling. The first is to sample individual subpatterns. We use edge sampling to form an odd cycle sampler, and we sample the center node first and then sample all the petals from the neighbors to form a star sampler. And the next step is to test the remaining edges between these subpatterns. For example, we already sampled the 5-cycle and 5-star subpattern. We will test whether the last remaining edge exists in the original graph to see whether it can form a pattern. And based on this, we can also calculate the sampling probability. These are the basic steps of graph decomposition sampling. And we also proposed system optimizations to accelerate the computation. The first is the failure probability-aware sampler scheduling, and also catching and reusing sampled subpatterns. Here we will focus on the first part, and please check more details in our paper. We found that different subpatterns have different sampling failure probabilities. Here, failure means a sampler does not find the pattern, or the sampled nodes and edges cannot form a pattern. Here is a 5-house example. It will be decomposed into a triangle and a 1-star. Here, 1-star here is just an edge. And we found that the triangle subpattern is more likely to fail, for example, with probability of 92%. And a 1-star will never fail because it's just an edge. Then the subpattern sampling order matters for the running time, because if a subpattern sampling fails, the entire pattern cannot form. Then we can early terminate the sampling trail if there are any failures. So based on this, we can schedule the more likely to fail subpattern to be sampled first. For example, if we sample the 1 star, the edge first, we will have 100% probability to sample the next subpattern, the triangle. And every computation needs to be performed. However, if we switch the sampling order, we sample the triangle first, we will only have 8% probability to sample the next subpattern 1 star, and then we save 92% computation when sampling the 1 star. In our evaluation, we found that it can help improve the performance by 2 times without affecting the sampling accuracy. Overall, based on the process, putting the system together, we have the Arya system implemented with multiple components. And here is the Arya workflow. We take the graph and the pattern as the input to Arya, and then through fractional edge cover linear programming solver, the pattern will be decomposed into all cycles and stars. Next, we need to configure the number of samplers needed to the Arya system. We give user 2 choices here. The first is user can give the system the error target they want, and the error-latency profile will estimate the number of samplers needed, or the user can directly configure the number of samplers based on the time they can tolerate. And next, the sampling engine with this number of sampler configuration, it will run the sampling trails in parallel. And finally, it will give out the estimated counting and sampled subgraphs. In the implementation, we have single machine Arya version and also distributed ones. In the distributed system implementation, we use OpenMP and MPI hybrid programming model and use memcached key-value store as a backend graph storage. We evaluated Arya on medium, large, and giant graphs, and also use patterns from simpler ones with 3 nodes to the more complex ones. And all the estimated results are within 5% error target for approximate systems. We compared Arya with exact mining systems. In the distributed replicated graph setting, we compare Arya with fractal and graph-phi system, and we show that Arya can have several hundreds times of speed up compared with some. And also in the large graph Twitter, we found that fractal and graph-phi, they either failed to complete the job within a day or they crashed during the computation. And in our comprehensive evaluation, we show that Arya runs up to 20,000 times faster than fractal and up to 1,000 times faster than graph-phi. We also compared Arya with approximate mining system ASAP in the single machine setting. In the YouTube graph with more complex pattern 5 holes and triangle, we show that Arya can give up to 150 times speed up. This is because 2 reasons. First, Arya needs less number of samplers than ASAP, or sometimes the number of samplers is similar as ASAP, but each Arya sampler runs faster because we use edge sampling. However, Arya does not always perform the best. In the friend-star graph, when mining the 4-motif pattern, we show that Arya runs slower than Peregrine and graph-phi system. These are 2 exact mining systems. This is because friend-star is a more sparse graph, and sampling-based approaches are hard to find pattern when the graph is sparse. For next steps, we plan to extend Arya to trailing edge graph scenarios, and also we can select the best graph pattern mining algorithm for different graph pattern inputs. As we see in the evaluation, there's no always winner for arbitrary graph pattern input. In conclusion, graph pattern mining is an important and challenging task. With larger and denser graphs and more complex and arbitrary patterns as the input, existing systems suffer from poor scalability issues. Arya leverages graph decomposition theory and sampling techniques for fast and scalable pattern mining. In the evaluation, it outperforms existing exact approximate pattern mining solutions by up to 5 orders of magnitude. We open sourced Arya at this GitHub repo, and this brings the end of the talk. Thank you for listening. I'm happy to take any questions.